Okay, so now let's look at the validation of the simple linear regression model. Okay, it is important to validate the regression model to ensure its validity and goodness of fit before it can be used for practical applications. Right? You need to understand that if there is actually if you want to understand if the model is actually performing well on the data, or if there is even any relationship between beta naught, beta 1 and y, right? Because if there's no relationship between beta 1 and y, and then there's no point, then there's no prediction available. Your model can't predict anything. So to validate that a relationship exists and it's a good relationship between your parameters and your regressor, we use some validation techniques. Okay, the first one is r squared, okay, which is coefficient of determination. It's also called coefficient of determination. And then there is hypothesis testing. Okay, and then there is analysis of variance, which is ANOVA for overall model validity. There's also residual analysis to validate whether the residuals actually follow a normal distribution, because that was one of our assumptions for the linear regression model, right? So there are lots of ways to and lots of techniques to validate the SLR model, which is the simple linear regression model. But in this video, I'll only stick to R square and hypothesis testing. Okay, so let's start with R square. So the primary objective of regression is to explain the variation in Y using the knowledge of X, right? We want to explain if how Y varies with respect to X, correct? Beta naught plus beta 1 X. The coefficient of determination measures the percentage of variation in y explained by the model beta naught plus beta 1. Okay, so r square measures the percentage of variation in y that is explained by the model. Okay, just read this sentence once again. Measures the percentage of variation in y that is explained by the model. This is in, yeah, bad handwriting. So just read this because you'll need to understand exactly what this statement means to understand what I'm going to do next. Okay. So the variation in yi, can be explained as beta naught plus beta 1 x plus some error, ei, right? So this is the total variation in y. Okay, total. This is the variation explained by the model. Model explains this variation. And this is the variation that is not explained by the model. Okay, not explained by model. Okay. So in the absence of the predict okay, so yeah, so now in the absence of a predictive model y I, okay, so let's say that I don't have a predictive model at all. I have my points yi, okay, these are all y's, okay, yi's, these are all the values of my yi's. Now I don't have any model to predict the value of yi. What do I do? If I have to give some value for a prediction, what do I do? I can build a very simple model, right? I can take the mean of all of these points, call it y bar, and I can give that as the output, right? So y bar is my output value in the absence of a model, correct? So we will, in the absence of a model, we will use yi, okay? So I can write the total variation as yi minus y bar, correct? Because if I don't have the model, then this will be my total variation. Um, and then this is basically the model explain variation is basically yi hat minus y bar, and the errors is basically I'll write it here, yi minus yi hat. Okay, so the total variation is the difference between the actual value and the mean value right here. The variation explained by the model is the difference between the estimated value of yi, which is the predicted value, and the mean value of y. And the variation that's not explained is the difference between the actual value yi minus the predicted value yi hat. Okay, so if you add all of this together, you would still get the same equation for the linear regression. Okay, so now it can be proved mathematically, that you can prove mathematically that that the total variation is equal to the sum of square of explained variation plus the sum of squares of unexplained variation. Okay, which basically means that I equals 1 to n yi minus y hat the whole square equals sigma I equals 1 to n yi hat minus y bar the whole square plus sigma I equals 1 to n yi minus y hat the whole square. This can be proven. Okay, basically I've just taken the square of all of these and summed it together. This can be proven. Okay, so the coefficient of determination is basically which is r square, is basically, now let's come back to this definition. It measures the percentage of variation in y that is explained by the model. Okay, so we want the variation that's explained by the model, yi hat minus y bar the whole square sigma whole upon the total variation. Okay, I equals 1 to n yi minus y mean. Okay, so this is what the coefficient of determination is. It explains the percentage of variation that is explained by the model. Okay, this is my variation of my model, and this is my total variation. So how much of that total variation was explained by a model, right? And the higher this value, the better it is, meaning that my model can explain the variation in the data set to a very large extent, right? If this is less, then it's bad. Okay, so coefficient of determination can also be written as R1 minus sigma yi minus y hat the whole square I equals 1 to n whole upon sigma I equals 1 to n upon yi minus y mean, y bar the whole square. Yeah, so it can also be explained by this. Okay, so this is basically nothing but the errors, the variation which is not explained by the model. Okay, this is sum of square errors. This is sum of square total. This is sum of square model. And this is sum of square residual, also called errors, right? So yeah, so this is just an algebraic equation where I've changed this to represent it in terms of errors, sum of square residuals. Okay, so this is how you explain or validate how well the model is performing using the coefficient of determination.